Okay, fine. See, in the last class we were looking at the pressure ratio, expression for the pressure ratio in terms of work done, CP, the compressor efficiency, and the inlet temperature. Okay. Now, if you look at this expression, actually, we have this T naught one. So T naught one is the absolute temperature. Okay. The same, this expression P naught 2 by PR1 is a pressure ratio in terms of stagnation pressures. So there are cases where, see, what exactly the compressor, this thing, say, if I have this, a compressor, okay, if I have this compressor, suppose this is one particular compressor, say a fluid enters at some velocity V1 and it exits at some velocity V2. Okay. If this is the case, so there is a static pressure and stagnation. There is static pressure plus some amount of kinetic energy. That means if I try to write it like P naught is equal to static pressure plus some V square by 2. So this is a rough estimation of your stagnation pressure, how you are going to calculate. Now, suppose see at the exit or at the inlet, say this is to atmosphere. From the atmosphere, I am trying to extract the air, or I am trying to exit, that is, the air will exit to a large container, something like a tank or something. What will happen? So your exit velocity will just nullify and it will become your exit, maybe the velocity, or it may become almost zero. So there are conditions where it may be static at the inlet or it can be static at the exit. So under these conditions, actually, so instead of this particular, maybe if I try with the stage pressure ratios, all those things, the same formula I can write in terms of static pressure. That will be P2 by P1 is equal to 1 plus W by Cp into compressor ratio divided by your static temperature divided by gamma minus 1. This is in terms of static components. In terms of static components. And also from the Euler's equation, from the, you go back and recall from your turbo machines course. So from the Euler's equation, I can write for W, that is the work that is done, I can write in terms of whole velocity VW2 into U2 minus VW1 into U1, where VW2 is the whole velocity at the exit and U2 is the velocity at the exit. And VW1 is the whole velocity at the inlet and U1 is the blade velocity at the inlet. Okay. Now, this is for a radial. This is for a radial flow compressor or centrifugal compressor. What will happen if I have an axial flow compressor? In that case, your U1 and U2 both are same, because I am going to calculate with respect to the mean diameter. So in that case, your W I can write for the Euler's equation. Your W will be equal to VW2 minus VW1 into U for an axial flow compressor. So for a radial flow compressor, that is the equation, and for an axial flow compressor, this will be the equation. So even under these conditions, we have certain special cases. Okay, we have certain special cases. That is, if my whirl at the inlet is zero, so I have a case. So a special case, I have a special case where at the inlet there is no whirl. I think for no whirl at the inlet. For the no whirl at the inlet. That means, what do you mean by it? My VW1 is equal to 0. So in that case, what will happen to your W? So therefore, your W will be only for, will be equal to VW2 into U2 for a radial flow compressor, and your W will be equal to VW2 into U for an axial flow compressor. That's all. This is going to change. Or I can write directly for these conditions, I can directly write the pressure ratios like this. P02 by P01 is equal to, in place of W, I can write VW2 into U2 divided by Cp into your compressor efficiency divided by P01 plus 1 plus 1 or 1 plus whatever it may be, whole to the power of gamma minus 1 gamma divided for a radial flow compressor, or I can write P02 by P01 is equal to VW2 into U divided by Cp into compressor efficiency divided by T01 plus 1 whole to the power of gamma by gamma minus 1. This is for an axial flow compressor. This is one particular case. So let's take cases actually. So let me call this as case A, where your inlet at the wall inlet is 0. So there are certain cases where your flow at the exit, that means your blade angle is exactly, that means radial exit condition. Okay, if I take the B actually, that is called as radial exit condition. What it is actually? That means if I try to draw the velocity triangle, it's something like this. See, I'm going to draw only the exit velocity triangle. This is my R2 or D2. So here, so I have a velocity. That means you are along the blade. Say, this is my blade. So this is my blade. Okay, I have a blade like this, and fluid is entering like this. So this is my blade, whatever I have. Okay, I'm just writing the blade, and you have your inlet. So this is my R1. This is my R1, and I have a blade in that direction. So along the blade, I will be having what is called as a relative velocity. That means if I try to draw the velocity triangle, so along the blade, I can write my VR2. Then in the flow direction, I'll be having the VF2. This is at the exit temple. So this will be my VF2. Then you have your absolute velocity, this direction. This will be my V2. And everything is covered. So I can close it. So this is my triangle. Okay, this is my triangle. So this will be my U2 or whatever it may be. And okay, that will be my U2. The total one will be U2. Okay, and only this component will be VW2, because this is the whirl component of your V2. Hope you remember, absolute velocity component has two things. One is the flow velocity, other one is the whirl velocity. So if I try to write the blade angles, this is my beta2, this will be your exit blade angle, and this will be your flow angle alpha 2. Now what will happen? See, if I tell that my radial exit conditions. So what I am trying to do actually, I am trying to pull this particular beta 2 so that my beta 2 becomes 90 degrees. So what I am going to end up with actually, if this is full, this VR2 will combine with VF2. So I will be getting a triangle something like this. So I will be having a triangle of this fashion. It is simply a right angle triangle like this. I am going to end up with a simple right angle triangle. This is my right angle triangle. So this will be VR2 is equal to VF2. This will be my V2. Okay. This is my beta 2, which is 90 degrees. And this is my alpha 2. And so this is my U2, which is also equal to VW2. Your VW2 is equal to U2. So what will happen under these conditions? So if I have, for a no whirl condition, VW1 is equal to 0. So the second condition is for no whirl and radial exit condition. For no whirl and radial exit, this here also is no whirl and the radial exit condition. What will happen? So if you look at it, my VW2 is equal to U2. So therefore, your W equation, what it was, VW2 into U2, either I can write in terms of VW2 square or it will be U2 square. Then what will happen to your equation? So therefore, my equation will become P02 by E01 is equal to, this will be simply U2 square by Cp into the compressor efficiency divided by P01 plus 1 whole to the power of gamma by gamma minus 1. So this will be your equation for, so what I'm telling about for radial flow compressor. I can have a similar thing for an axial flow compressor, but for an axial flow compressor, what will happen? You don't have any radial liquidation. There the flow is axial in nature. So this is only a special case for a radial flow condition. But there you can have only the whirl can be zero. That is with a no whirl condition. That means your VW1 can be zero. So the equation will be simply VW2 into U2, VW2 into U. And I don't have any radial exit condition for a axial flow compressor. This is only for centrifugal compressor or a radial flow compressor. Only for RFC, that is the radial flow compressor or the centrifugal compressors. Okay. Now, once you have seen this equation we have actually, there are certain factors which are going to affect your radial flow compression, your compressors. Okay. So we'll try to look into that. What are the factors which will affect this? See, if you take any kind of compressor, actually, what we see actually, whenever we try to compress the air, so in the multi-stage compression, okay, in compressors, so especially compressors with stage compression, in compressors with stage compression, what we see is actually we need to, so we will end up at what will happen? A rise in temperature. A rise in temperature is the phenomena what we see actually. Our desirable is actually we need to, desirable is to reduce this temperature. Reduce this temperature. Whatever the temperature we see, we have to reduce it. How we can do that actually? This is something like I have to reduce the number of stages, or I can call it as, rather calling it as reducing, optimizing the number of stages. Optimizing the number of stages. Now, how we can do this actually? This optimizing the number of stages can be done by considering the overall pressure ratio. Okay. When you look all these things actually, the designer, maybe required what, maybe a compressor blade designer or the blade, we can the whole compressor designer. So he has to consider some of the major aspects actually. So the designer, a designer or the blade designer, a compressor designer has to consider the following things. One is the blade speed, which is very critical. Okay. Then the second thing is the axial velocity of the fluid. The axial velocity of the fluid. And then the third one is, which is very critical, which is called as deflection, fluid deflection. Okay. Which is called as the fluid deflection, which is actually a difference of your blade angles. Okay. So difference of your blade angles. So beta 1 minus beta 2 or beta 2 minus beta 2. Okay. This is called as a fluid deflection. So this is only with respect to the rotor blades, not with respect to stator blades. Okay. So now, what will happen if my blade speed is on the higher side? If blade speed is very high, I will end up with an uncontrolled blade speed and an uncontrolled speed of the rotating. That is, your n will increase like anything. So we should avoid the high blade speed, axial velocity, the fluid or the steam jet, sorry, air or whatever it may be, steam or a working fluid. We take it, maybe if I go with a compressed turbine, all those things, and turbine and all, it's high temperature. It's only compressor, it is air. So there, the axial flow of the fluid or the air, we have to ensure that it is not very high. A very high axial velocity of the jet will damage your blades. And the second thing is a high fluid deflection. If a difference between the beta 1 and beta 2 or beta 2 minus beta 1 on the rotor blades, if it is very high, that also will create. So all these things actually, this three will create what is called as blade stresses. Okay. So when you have this actually, all this, the blade stresses. When you have a blade stresses, actually, this will limit the blade speed. This will limit your blade speed. Okay. Now, what is the effect of it? It will have an effect on your beta. When the blade stresses, so it will have an effect on your beta. So what is beta? Blade angles and all, it will have an impact on, see, if you try to look into it actually, this is nothing but completely having an effect on your aerodynamic. Okay, aerodynamic system or aerodynamic considerations, what we call. That means giving the shape of that particular blade. So everything, and this will see when you try to give this to this aerodynamic this. So what we have is actually a pressure gradient. Hope you remember in the advanced fluid mechanics, we had two types of pressure gradients. One being the adverse pressure gradient, one is the favorable pressure gradient. Okay, so all these things will lead to high blade stresses. If blade stresses are kept under control, then it will have an impact. So maybe you will have the speed under control, the aerodynamic, the whole shape is under control. Maybe the pressure gradient also will be under control. All those things are there. Now, as I told, blade speed. Okay. Now, the centrifugal stresses in the rotor blade depends on this rotational speed. What is it actually? Why it is actually? You know this. Your U is equal to pi d n by 60. So the blade material, see here, if this U value is increasing like anything, it will have an impact on your n also. So if you want to consider that actually, then you have to be very careful with your blade material. I can't go with a low cost material if the speed is very high. Not only the blade material, if the speed is very high, so I have that restriction on the length of the blade. Length of the blade, I do have a restriction on it. I can't go for a longer blades. If I go for a longer blades, what will happen? It may lead to centrifugal tensile stresses. Go back to your strength of materials and all. So look at the specimen here. You have to look at the ASTM standards. So the tensile stresses will make your blade to fail under buckling conditions. Because the blades are like a cantilever. They are almost like fixed at one particular rotor end and other end is free. So the root of the blade becomes very, very critical. Okay, the stress actually, so we need to look at the centrifugal stress under these conditions. So we have to look at the centrifugal, okay, centrifugal tensile stress. Centrifugal tensile stress at the root of the blade. This becomes very critical for us. Okay, so if I take something like tensile stress as this thing, so from max, okay, here it depends on, so this is given by some formula there, that is the density of the blade and your rotational speed. So then divided by your cross-sectional area. Okay. So now this has to be, this is something like a constant. So now this has to be, see, this particular value depends on your root to tip of the blade. I need to look into this particular thing. A, that is your cross-sectional area. Okay. A is the cross-sectional area. Yes. And I have to integrate between your the radius from root to tip. Just I'm trying to write a general equation. Okay. Blade density, your angular velocity, your cross-sectional area. Okay. Your cross-sectional area. So this plays a very, very important role. Then if I try to look at this, so if the root to tip, this particular thing, so maybe to be what they try to do is actually maybe they try to keep this as simple as possible. Okay, maybe the cross-sectional area they will take it as maybe pi r1 square minus r2 square. Okay, pi r1 square minus r2 square. So that's how they take and they try to calculate it. That's it, very simple. R1 square minus R2 square R. So D1 square minus D2 square by 4 pi into D1 square minus D2 square by 4, something like that actually. Now, this area is there, no? So if I try to write this particular thing, a cross-sectional area, so some books actually they try to call that as, see, this is cross-sectional area. This they call it as annulus area. Annulus area. What is this annulus area? That means if I take this particular thing, okay, and if I take this particular thing, so this is your annulus area where your fluid is flowing. 2 pi r something circumference, depending upon 2 pi r this particular thing, I need to look at. So this A is your annulus area and ACS is nothing but your cross sectional area, which will be just pi d square by 4 or pi r square, whatever. So here, this annulus area becomes very critical when I'm trying to. So if suppose the root to tip is bigger, that means if I go for a higher length blades, then this particular A will become bigger. I have low, maybe even for the same blade material, so that becomes critical for me. Is that clear? So now, at any given point, I need to ensure that this value is within the limits actually. This value is within the limits. So why this limit is there? Because the maximum stress what we are trying to get, they are all centrifugal in nature, and the centrifugal stresses away from the radius, away from your axis. As I move away from it, actually at a very high speed, they becomes very critical. And I myself have seen in test beds where it was very critical that. So where some of the rotors or maybe your compressor blades have come out from the test bed. Okay. To be very precise, they call that as hub to tip ratio. Okay, hub to tip ratio. It has to be, see, maybe if I try to be very specific with that. So this hub to tip ratio should be proportional to the your tip speed. Okay, what it is? Pi dn. I can write in terms of d by 2. So this will become pi 2r into n. So your u is proportional to your r. So when I try to look at it, actually, your omega is 2 pi n by 60. So your critical stress becomes directly proportional to, that means your centrifugal stresses. So your centrifugal stresses are proportional to u square. Omega square means actually n square. So it is actually proportional to your tip speed or omega square or u square, whatever it may be. And the reduction in that particular, see, if I try to reduce the hub to tip ratio, it will increase your blade speed. So indirectly look at it. If I try to reduce that hub to tip ratio, if I try to, that means you have to optimize that. If you don't optimize that value, if I try to If that particular thing is reduced actually without drastically, then automatically you can see that the blade stresses or your centrifugal stresses will increase. They are maybe inversely to that actually. Okay. To be very maybe in practical, what will happen? Let me tell you. So in practice, when I try to design a centrifugal compressor or a axial flow compressor, what they take is actually they're going to take a particular blade sectional area. That particular blade section, they're going to reduce it actually. Okay. That means in practice, I'm telling. This is my experience. What I was in the time, maybe the compressor team when I was in GE. What they do it actually, they used to the blade sectional area. Okay, the blade sectional area is slightly decreased with the radius to relieve the blade root stress. Okay, what do you mean by it actually? The blade, let me write that. So in practice, the blade sectional area is decreased or reduced, okay, with radius. That means along the radius, with or along the radius. Okay, with radius. It is reduced with radius to relieve the stress from the root of the blade, from the root. Okay, and this we call it as loading. So what will happen actually if you do this particular thing? The loading on the disc actually. So usually all these things are attached. Actually, all the things are loaded. We call that as a loading. Okay, so the loading on the disc carrying this particular blades is equally distributed or released or reduced. So to get that kind of an effect, actually, they do this. So that's why if you see any kind of a blades, actually, this is what they do. This is in practice. This is practice. So this has to be iterated once or twice. It has to be iterated, and they come up with some kind of a constant. They try to fit an equation. Okay, equation and means some kind of a polynomial equation they're going to fit it, and that equation come up with some kind of a range for a constant. Okay, they will try to fix the range for a constant. So that range may vary from 0.4 or 0.5 or zero point 0.6, something like that. So it is blade specific. So for one of the blade it is maybe 0.4, and one of the blade it may be 0.6. Okay, all the things actually will reduce to, all these things are done to reduce your, maybe what we call it as maybe your centrifugal stresses. So roughly what will be the tip speed? Do you have any idea, anyone? Roughly, most of the compressors, axial flow compressor or anything, from the aerodynamic vibration perspective and all. So the tip speed, what we could see in most of the blades is around 350 meters per second. It's a very critical. So that's a critical. See, if you look at it, your critical speed, U critical, this is your critical, will be roughly around 350 meters per second. So it depends on, see, depends upon your, see, this particular thing depends on, once again I told that this depends on your annulus. Suppose this speed is more than 350, then I can't run at those speeds actually. See, if your tip speed is 450, and maybe if you might have seen that in turbo fans, if you want, you can just look into it actually. Turbo fans, that's one particular thing where you have what is called as high bypass ratio, because part of the air is goes into the compressor. Maybe most of the some of the aviation gas turbine engines actually, they work on what is called as high bypass ratio turbofans. What they do is actually a part of the air will go into the compressor, rest will simply bypass your engine. Okay, that design we call it as high bypass ratio turbofans. So especially in high bypass bypass turbofans. Okay, so where your tip speed will be slightly above your 350 meters per second, but the majority of the gas, majority of the air that is sucked in will not enter your compressor, but maybe 20% or 30% may, there maybe 70% will be just simply bypassing your compressor plates. Okay. Any doubts here?
No, sir.
Okay, fine. Now, one more thing which affects your blade or your maybe the design and all is your what we call it as maybe the axial velocity. The second one, as I told, the first one is the blade speed. I told the axial velocity. So the axial velocity, if you look into it, axial velocity, if I try to uh, plot with respect to something, the second one is axial velocity. The axial velocity, and these are all compressors actually. So if I try to plot something like this, plot your the velocity in this. So this is your blade speed on your x-axis, and maybe if I try to take a relative Mach number on my y-axis, okay, so write the Mach number maybe 0.6 or 0.7, something like that, 0.6, 0.8, 1, 1.2, anyhow, you don't have more than that. So around 1.2 or 1.2, or it can go up to 1.4. Okay, up to 1.4. 1.4 around that I will be going actually. Now, here what will happen actually if I try to draw a simple velocity triangle? So what is it actually? If I try to draw a triangle, this will be your blade velocity. Okay. Now, what I want to do if this is, I try to draw your what we call it as some V1, I am going to close this triangle with your the relative velocity. Okay, the relative velocity may be VR. Now, what I'm trying to do, say for example, hope you remember that in your turbo machines course, you might have done that. There is an IGV, okay, that is guide vanes. Okay, so what is the purpose of this particular guide vanes? When I try to have these guide vanes, what will happen? This guide vanes, if this particular relative velocity, if it is exact, this is 90 degrees. That means your VR R will be equal to your V flow or whatever it means. That's how we try to design it. We want it to be. Suppose if you are, okay, suppose if if there is a little bit of guide vanes is there, if I use a guide vane IGV, my V1 will become smaller, and this is what I'm going to show. So what will happen? I could see a reduction in my velocity due to the IGV guide vanes. Okay, reduction in that particular thing due to guide vanes. Okay, these IGV or these guide vanes, what we call, so they are all aerodynamically necessary to reduce the see what exactly is IGV will do. This IGV is nothing but those things will try to operate in and around your transonic Mach numbers. They try to operate in and around your transonic Mach numbers. Hope you remember something called as maybe your strip effect, all those things and all. So what will happen? These guide vanes, how they do is actually to be very precise. If suppose this is my uh, blade actually, just I'm going to type the blade. So this is the tip of the blade. Okay. So what will happen? Maybe at the back of this particular thing, I could see there is a shock kind of thing which is formed. Okay, a shock kind of a thing is formed because this is my velocity. What I could see, this is the velocity, absolute fluid velocities. So this guide may see, or maybe you might have heard of something called as pre-whirling. So pre-whirling is nothing but I'm going to give Sarsi. I'm going to give little bit of whirl to it. I'm going to give little bit of induced whirl component. Otherwise, my BW1 is equal to 0. I don't have any whirl component. So what is the overall thing actually? The overall thing, this will reduce your V1. A small quantity, it's a penalty what we are trying to find actually. But maybe the what advantage we are going to see actually. The advantage actually here, why this particular thing is actually here there is a less pressure because I need to create the suction here. Here I have a little bit of high pressure. It's not very high, I'm telling. There is a little bit of delta P here. And this delta P is very critical in getting this kind of an, what we call it as the breakaway of the fluid, maybe air or whatever it may be. And there are situations where the blades are failed because of the shock, because of the shock. So shock will, if there is a formation of shock there, so there is always a maybe some kind of a damage caused to the blade. To avoid all these things actually, what they try to do actually, they try to include this or maybe add this intermediate guide vanes or IGVs, what we call, in your entry to your compressors. Okay. Now, if I have a some kind of an IGV to that, what will happen? Your say upon 0.8 Mach number, and also this is what this is how maybe roughly it is not a complete 45-degree line, maybe slightly. So these are the lines what I'm going to get. So this is for one velocity, and I may be getting for one more velocity. Some three velocities I'll try to show. So what I see at the top, maybe if I take this as some V1 is equal to some 200 meters per second, this maybe V1 is equal to something around 180 or 175 meters per second. This may be velocity at 150 meters per second. So what is the effect we are going to see? This may be at some atmospheric temperature. So if here my VC, this is if I tell that the moment if I tell that VW1 is equal to 0, I'm going to get that triangle. So maybe with the dark color. So if the IGV is brought in, so there is no whirl. See, there is a little bit of whirl component added to it actually. The penalty what we are trying to do is actually, if you go and look at that equation, work done is equal to VW2 into U2 whereas VW1 into U1. So the work done quantity will get reduced, but I'll be saving the blade. I'll be saving the blade with a lesser, maybe a small reduction in your axial velocity. So this is what we could see actually. The relative Mach number. See, at this is all these things happening at the rotor entry. All is happening at the rotor entry. And this is specifically done for most of the axial flow compressors. Axial flow compressors it is done. And this will lead to what is called as, maybe you might have come across what is called as slip actually. You might have come across what is called as a slip. This will maybe the same phenomena happens at the exit. Okay, the same phenomena happens at the exit. The third condition, what I told, deflection, fluid deflection. That means what will happen if my beta 2 effect of increasing my fluid deflections. If beta 2 is increased or decreased, that will lead to what is called as, you might have studied in your maybe undergraduate turbo machines course, what is called as slip or slip factor. Okay, the slip factor, what will happen to the slip actually? The slip will reduce your power input or power requirement will get reduced. Okay. So let me write that. The effect of the third effect, it is actually the effect of your blade deflection. Effect of blade deflection. So what they do actually here, if suppose I'm going to fix my beta 1 and I'll be varying my beta 2. Beta 1 is fixed and beta 2 is varied. Okay, so beta 1 is fixed and beta 2 is varied, or it is modified, so that I can reduce this fix. What will happen under this condition? How will be my velocity triangle at the exit? If this is my velocity triangle at the exit, I'll redraw this velocity triangle, whatever I draw earlier, whatever I drew earlier. So this is my velocity triangle. This is my U2. This is my VF2, V2, and okay, this is my VF2, and this is my VW2. So this is my U2. So this is how velocity triangle will look like. Now, what will happen under this condition? If this is my alpha 2, this is my beta 2. Okay. So if my beta 2 is changed, deflection. If my beta 2 is changed, what will happen? That means this particular beta 2 is going in this direction. Whether the beta 2 is increased or decreased. Overall, it will have an impact on your blade velocity U2. I could clearly see that it will have an impact on your U2. One particular thing. Okay. It's increasing the, if I increase the blade deflection, what will happen? It will have an impact on this particular U2. What is its impact on your VW? Indirectly, see, indirectly, if you look at it, see, U2 or whatever it may be, this will have an impact on your, see, if I have this W actually, VW2 to U2, automatically this will have an impact on work done. Work done gets affected because of the changes in my deflection angles. Okay, so deflection angle, that is your blade beta 2 or something. So that particular thing will have an impact on your work requirement. So the work requirement, see, so I can easily calculate VW2 depending upon your W, depending upon my U or U2, whatever it may be. This is one thing. And the second thing is actually, so if there is a reduction in your alpha, okay, what will happen if there is reduction in my alpha, or the increase in this, so it will have an impact on your VW2. So deflection angles means blade deflection as well as fluid deflection. See, blade deflection is with respect to betas, blade angles beta 2, and also effect of the fluid deflection. Effect of the fluid deflection. That is your alpha 2. So this will lead to what is called as slip. Why? My VW2 gets reduced, and this will bring down your dam. Okay, one being the tip velocity, the second one being your axial flow velocity, and the third being your deflection, or your blade deflection, or your flow deflection, whatever. So all these things will, so these are some of the impact what we will be trying to look into to understand your